Okay, so as we know, chapter 4 is going to be about organic chemistry. Okay, so chapter 4. Oops. Organic. Okay, here is what you need to know list-wise from chapter 4. Okay. Nomenclature. When I say that, I mean okay. You need to know how to, and when I say IUPAC, just that's pretty much formal, okay? Formal naming, and then condensed, okay? When I say condensed, what I mean from that is those two things are either going to present it to you as a formal naming, and then you either have to find from the pictures he's provided the skeletal structure of said image, of said formal name, or you're going to be given the condensed and you have to turn it into the condensed skeletal, and you have to provide the IUPAC name. So they could go either way. Okay, so you'll either be given an image and then have to provide the name, or you'll be given the name and you'll have to provide the image. Okay. Also with condensed, you'll be given just normal condensed formulas, and you're going to have to again pick the structure that he's condensed. Okay, kind of like what Mastering Chem made you do. Okay, so that's for nomenclature. You also need to know in chapter 4, obviously, you need to know functional groups. Okay, from here, you need to know them. You need to be able to name them. You need to be able to find them. Slash, now I'm going to say draw, but you're not really drawing for the exam, right? Because nothing structurally for this exam has changed, and it won't change for the remainder of the semester. Everything is going to be multiple choice. But when I say draw, what I'm saying is he's going to give you an image, okay? And so he's gonna pretend that you could be drawing, but it's already done for you. How would you draw it, right? Does that make sense? Okay. So all three of those things in terms of functional groups. And then also for organic chemistry, you need to know about isomers. Okay, so you need to know about actually, I'm going to list it. Grace, will you still help me with that? So
yeah, I'll do it.
Okay, thank you. Structural, we're going to have an enantiomer. Okay. These also, we just want to let you know, your favorite thing in the whole wide world, chemistry has a million names for the same thing. I don't know why they do that to us, but they do. It's like, it really, so when people ever say tomato, tomato, you can't really banter back with them because it's like a thing. It's like a real thing, you know? So anyway, for isomers, we have structural, okay, which is also known as constitutional, all right? And then you have enantiomers, and then you have the subset of an enantiomer, which is a diastereomer, okay? Key things to know about this, so I'm just gonna kind of put a little side note. Steri or steric, okay, is something that I want you to kind of get used to because this is what helps us when we're dealing with chirality. Okay, and so anytime you have a steric site, it's like almost we're trying to determine if it could be chiral, right? You're also going to hear the term optically active, steric, chiral. Okay, they're all like the same thing. Again, tomato, tomato, but it's just making sure that you're aware what we're talking about, okay? It's all based on how and what you're looking for specifically, because when we're starting to deal with chirality, we're dealing with spatial. So the reason that I like to call isomers structural rather than constitutional, because the enantiomer and the diastereomer, these ones are spatial. Okay. And that's really, really, really important. So that's how you can tell the difference between what we're looking at. One, we're just looking at the difference, the change in the structure, okay? The second one is, where is it? Where is it spatially, okay? So that's pretty much the two subsets of isomers. You're either looking at it structurally or you're looking at it spatially. And how and what is it doing in space and how it orients itself and how does it spin? How does that change, okay? And how does that vary between molecule to molecule, okay? And then also for chapter 4, you'll have to make sure I cover everything correctly. Okay, so we talked about it here, but I'll just make it a subset too. Chirality. Because even though we talk about that in terms of a diastereomer and an enantiomer, I want you to think of that as, that's more like a specific portion of chirality, kind of. It's very interesting to think of it. But in this case, I want you to focus as chirality as its own entity too, because when you're looking at a hydrocarbon chain, there might not be really anything that we're looking at in terms of it. Is it an enantiomer or a diastereomer? That might not even be something that we need to know, right? Because there's not a lot of reactive sites in terms of a hydrocarbon for the most part. If it's just hydrogen and carbon, there's really no chiral centers. It's only when we add a halide, right, or something super electronegative that can kind of change the center of that. And then from there, we could say, okay, well, if we continue to add electronegative atoms to a hydrocarbon or, you know, a carbon chain, what is that going to change in terms of its orientation in its spatial, in space, okay? Okay. Then the last thing, in terms of chirality too, I just want to make note, you're going to have to be able to understand the term, understand/define it, and then you're also going to have to find/identify within a molecule. Okay. Okay, and then we're needing to do vocab. So in terms of vocab, what you really need to make sure you are familiar with, okay, proton. And then I'm also going to say H+, okay, because we called they're interchangeable, right? So I just want you to be aware that when I'm referring to a proton, that I'm also referring to an H+, okay? It's not just like from the periodic table. It's beyond that. We're now referring it explicitly to hydrogens, okay? Because we're going to do a lot of reactions, and with that, this guy is the reason why those reactions occur, okay? So proton, you need to know okay. So we have something, when we talk about carbon and organic chemistry, we're really referring to carbons in general, just anything that's predominantly native carbon, okay? That's organic chemistry, because that's what most of our body is made of. That's what the world's made of. It's all carbon, okay? Carbon, this term is kind of pronounced a little wonky. Some people say it's carbonyl. Some people call it carbonyl, okay? Again, I want you to just be very aware that this particularly is the bond, a double bond between a carbon and an oxygen. But then if somebody were returning to carbonyl chemistry, they're talking about carbon chemistry, okay? Or they also could be talking about carbon chemistry that has a lot of C double bond O's, well, with carbonyl, okay? So carbonyl, carbonyl, when you're taking the test and nobody's reading these questions to you, or you don't have an opportunity to ask what like, hey, can you read this question to me, or what this word is? I just want you to be aware of what that is here now, okay? So technically, for the sake of this portion of the test, I want you to know this as only as a carbonyl, which is a C double bonded O, okay? And because that's really what's going to be the most important thing when it comes to identifying functional groups, okay? Hydrocarbon is, like I said up there, it's just CHs, okay? So that's all that is just carbons and hydrogens together, okay? Other vocab that you need to know. And we'll talk about this when we get in terms of our functional groups, but an aromatic versus a benzene, guess what? They're the same exact thing. However, when I say that, they're the same exact thing for your portion of the exam, okay? But I would, if I were you, hint, hint, I would get in the habit of calling it just an aromatic versus a benzene, because I really feel that a lot of students are going to get confused when we talk about when we're naming. So they'll get confused with methyl, ethyl, propyl, butyl. And for some reason, their mind just really goes into what the heck is a benzene? And I don't understand, okay? But obviously we know that alkene, that's where we get that, which is indicative that there's double bonds places. So for the sake of just test anxiety, I would suggest keeping it as an aromatic, and you can call it as an aromatic ring, right? Or we have a benzene ring. I preferably like calling it an aromatic because this is what it might look like, or it might look like this, okay? And the reason we call that's where the term, this circle inside of the ring is where we get the term aromatic, because if we were to zoom in, and I'll make my structure bigger. These are electrons, and the electrons are just jumping to pi orbitals. And so they're constantly making what appears to be a circle. And so that's how we shorthand it as a chemist, okay? So I like this the best because when you see this image, for some reason, again, students don't remember that that's a benzene ring, but aromatic, it does ring a bell. So again, whatever floats your boat. If you're used to calling it a benzene ring from other classes you've had, then you can keep doing that. But I'm just trying to think about test anxiety. I strongly recommend you learn it as an aromatic, okay? But if you know it's an aromatic and it's not a list on the multiple choice and he puts benzene, which sometimes, hint, hint, he will to throw you off, that might also be a thing. If you're 100% sure it's an aromatic ring, but you don't see the word aromatic, but you see benzene, then that's what you select, okay? But I just want you to know that they're the same thing, okay? And then the last piece of terms, vocabs for chapter 4, I think oh, yeah. Again, another thing for functional group, and we'll get in there. I want you to be aware of what a phenol is, okay? That's a phenol, okay? What is this?
It's an alcohol.
Mm-hmm. Okay, phenol is going to be an aromatic ring with that alcohol, okay? Otherwise, if any alcohol is on a cyclic, no special name, okay? It's just an alcohol. Okay, so don't confuse those. It has to be on an aromatic, a saturated ring, okay? Another question he may ask you is this reactive, or is this really reactive or non-reactive? What do you guys think? Do we think that this is super reactive or non-reactive? I can't tell if people are shaking their heads or they're not shaking their heads or lost.
Aren't aromatic the cyclo alkanes fairly non-reactive in general because the bonds kind of hold together. I don't know about the floating around electrons though, so.
Okay, same thing, the same thing goes, okay? Cyclics and aromatics are very stable, okay? They're super stable for the same reason is, why would I go in here and break a ring? Because when we have a ring, all the pressure, everything is of equal distance to each other. And so we're pretty spaced out. That's why we get a nice shape, okay? It's just automatically our angles are nice in cyclics, and it's allocating enough distance between those electrons, okay? For an aromatic, now that we have double the electrons, we've got more electrons in there and they're spinning around. Do you think, you have to think about it in terms of, can something come in and rip that apart? Probably not. What is stronger than 3 double bonds oscillating inside of a circle? Okay, not gonna happen, right? So these are super stable, okay? So he may ask you a trick question. These are super stable, all right? All of them, okay? Okay. All righty. Now we're going to go to chapter 5 and tell you what you need to know from chapter 5. Okay, so chapter 5 is reactions, and particularly like those chemical reactions dealing with organic substances and organic molecules. Okay, keep in mind, it's organic. Okay, organic, organic, organic. It's all organic. So when we're dealing with organic reactions, we're predominantly going to be working with water. And usually it's a strong acid. Okay. Why do you think it's a strong acid? No thoughts? What did I say was, oh, go ahead.
Hydrogens.
Hydrogens, okay? Anywhere we can get a hydrogen, that's what we're going to be working with, okay? So you're going to see it always in the strong acid, and you're going to be dealing it with water, okay? Strong because we need to have something strong enough to go in and break a bond, because water is not that guy. Water is not going to make, he'll make and break hydrogen bonds, yes, but he's not going to go in and attack something, okay? He's not a bully. He's just a user. So you need a bully to go in there. That's what the acid does. And then water uses, okay? So for this, the things that we need to be aware of first, okay, is our favorite: oxidation, reduction. Second, hydration. Third, hydrolysis. Fourth, hydrogenation. And then you need to know condensation. Okay. And combustion. That looks like a lot. All right, it really looks like a lot. Like there's a lot of little details that you need to know, but I'm going to tell you right now, what I read on this paper is all you need to know for these reactions, okay? And so I'm going to do it in red. For combustion, what you need to know. L means for left side. Left side of a chemical reaction, you need to see this, C, and then I'm going to put just X and Y because it could be any amount. So you better see some sort of CH, what do we call that?
Hydrocarbon.
Good. Get used to start saying these words out loud, okay? Don't call them carbon chains. Get used to saying hydrocarbon, because when you take this exam and you take the final, you'll be aware of these words. So you're gonna have to be, this is the formula for combustion. CXHY and always O2. Always. If you don't see an O2, but you see a hydrocarbon, that's not combustion, all right? Dead giveaway, look for the O2. Second thing to look for is the CH, okay? Any sort of hydrocarbon. If the O2 is present and then the CH, the hydrocarbon, is not present, it's not combustion, okay? We're doing oxidation then. Do you see how the two things to make this a combustion reaction are? Because when we start talking about oxidation, you're going to be taught, I'm going to teach you 3 ways to identify easily oxidation reduction, and oxygen is one of them, okay? And O2 is a great source of oxygen, but that doesn't mean that we would be having a combustion reaction. So you need to have those 2, but even more so, the easiest way to identify too is by CO2 and water, okay? Your reaction has to look like this. You can have any other weird stuff in solution, but or attached to your hydrocarbon, okay? But realistically, this is what it looks like, because you're not going to get the products without a good hydrocarbon, okay? It doesn't matter how many carbons. It could be 2 carbons, and it could be 6 hydrogens, or it could be like 32 carbons and then 100 and something hydrogens. It doesn't matter, okay? So that's combustion. This is on the right side, so the products. Okay, condensation. When we're having when a condensation reaction is taking place, what's the first thing that we think about? Right off the rip, you should be thinking about what? Who's the culprit of this reaction?
Water is in the product.
Water's in the product, okay? So water's the issue here. Water's the main guy. So what we have in a condensation reaction is that if water is on the product, does that mean he was once in the molecule and is leaving, or was he used and part of the reactants, and then he just ends up to be left over in the product? Do we know?
In condensation, he's in each of those things and then comes out.
Right. So exactly. So what that means is there was a source of OH. Okay. There was an alcohol present somewhere and a free hydrogen somewhere on these molecules that we can rip apart, take off to take 2, we're taking 2 molecules, 2 small organic molecules, and we're breaking them into 1. So the key takeaway here is you have 2 small, and I'm going to say OG for organic, okay? 2 small organic molecules that come together I'll do an equal sign this way, to 1 molecule plus water. Okay, so here's how he can ask you, what is the product, the end result of a condensation reaction? Then he could give you multiple choice, and he could say one large organic molecule plus water, or he could trick you and say two large organic molecules plus water, but it's not going to ever be 2, right? Because we're taking 2 and we're making 1, so it goes 2 to 1. All right, so you have 2 on the right side and you're going to 1 on the left side. Okay, also, this is never usually listed. Okay, what I mean by that is when he's doing a reaction, you're probably not going to see water on the right hand side. You're going to have to just observe that, oh, we had 2 things on this left side of the chemical reaction, and now we only have 1, but I can clearly see what's happening here and how we came together, so I can safely say in this chapter, it's going to be water left, okay? But we don't ever list it. Cool? Okay, I'm going to go to its opposite, which is hydrolysis, meaning to cut. So if we're cutting with hydro water, then we're going to have 1 large molecule. Okay, and he's then going to go into 2 small. Note, 1 large OG plus water. Now this one will be written in, okay? He will be written in. He'll either be written in above the arrow. So when we get to practice one of those, he'll be written above the arrow, or he'll be written in actually by there. So it'll be like, I don't know, could be butane plus and then water, okay? But you know that he'll be noticed, he'll be written in there for your exam. Okay, any questions so far? No questions? Okay. Now we got to go into a hydration reaction. Okay. Key takeaway here is you're having an alkene. Alkene, and you have to have an alkene and you have to have water. So alkene double bond. You have to have a double bond with this to be a hydration reaction. So please do not select an option for multiple choice that is hydration unless you see a double bond in that picture. Okay, because he will throw hydration at you and he will throw hydrogenation at you when it really should be hydrolysis. Okay, because they're all hydro. Okay, if you don't see a double bond in there, stay the heck away from hydration. Okay. The product of this is always going to be an alcohol. Okay, and that makes sense. When I do an example for that, you'll see why. But if you think about it, H, and notice how I'm drawing HOH when I write water out. Get in the habit of doing that, especially for this test, because you're going to be able to see exactly what your products are. You're going to look at that and say, oh, I already know that I'm making an OH, because why? I have a double bond, which is 4 pairs of electrons, and then I have H pluses, and wherever there's a minus, a plus goes. So basically, I'm adding hydrogens to those. When I remove the double bond, I'm adding something there, removing something, and I'm going to be making an alcohol, okay? Because when we remove electrons, do we get more positive or more negative when we remove electrons?
More positive.
Right, so this is going to be like this. Okay, and then remember I have this in solution. Okay, and I have a lot of that in solution. Okay, so now that I have this carbon and this carbon that lost, this carbon currently has 1 other H to it, and this carbon has 2 other H's to it at this time. Okay, and they shared that double bond, which is what made them all happy. But now we have a positive, so this guy, water, is going to attach here, but that OH from water, that OH from the water is going to be what makes us the alcohol. Okay, and then we're just left with this in solution, and that's fine because we have a bunch of water in solution, so it's just going to keep dissociating and associating, et cetera, and then we'll know that this will become and can add on here. Okay, so that's how we saturate and satiate a molecule. Okay, electrons leave, we're more positive, a negative is going to come in, counter that positive. That negative is always OH. That's why we make an alcohol, you see? That's why the product is always an alcohol. And we'll do nicer examples. Okay, the last thing is hydrogenation. And the key thing for a hydrogenation reaction, I'm going to write him in a different color because I'm kind of getting crazy here, is always going to be H2 over either platinum or palladium, okay? And that, my friends, is a metal catalyst, which makes sense because H2 can't do stuff, right? So what do you think we're doing here? I'll tell you. On your left side, and I'll zoom out in just a minute. On the left side, you're going to always have an alkene. And then you're going to see this. And I'm going to put a backslash because I'm going to BD, but it's either going to say H2PT or H2PD, okay? So hydrogen gas and palladium or platinum. So either way, all right, but not together, just so you know. And then what are we doing? Well, that's what we're doing. So what are we doing? Okay. So Hydrogenation, removing the alkene only with H2 palladium or H2 platinum. All right, notice how there's no H2O, there's no OH source, it's just hydrogen gas. So all we can do is remove the alkene, okay? But in a hydration, we are removing the alkene to add an alcohol, which serves for the point, serves at a later date for a source of water, because that's how we make water from alcohol, right? And that makes sense when we're talking about our condensation reactions. We're basically removing alcohols and from an ester, and that's how we make water, okay? So they're all very similar. It's just what's happening where and how to quickly identify. And this will be the fastest way for you to identify that. Okay, and then oxidation reduction, I'm actually just gonna highlight this guy. I'm not gonna define it up here because it's kind of hefty and it has a threefold definition for the sake of this class. So I'm not going to do that here. Here you go. Okay, any questions? Moving too fast? Are we okay? Okay. This is why I like to do 2 back-to-back reviews, because the first night is going to be preparing you with an outline of what you need to know, okay? And minor examples, and then tomorrow is always gonna just be pretty much examples and things that you'll be seeing on the exam via questions asked, okay? I know it's a lot to ask you to sit with me for 2 hours sometimes, but for 2 days, but trust me, it's the best way. Okay, so that's it. Oxidation reduction, we're gonna go ahead and define right now for you. Okay, threefold definition. Here's the first part. Oxygen. Here's the second part. Hydrogen. Here's the third part. Electrons. All right. First part, lose, gain, lose, gain, lose, gain. Okay, before we go in there, I'm going to make a big note. Reactants, always this. Key takeaway. Okay. He's going to use the term, which one of these is the oxidizing agent? Which one of these is the reducing agent? Please don't provide something that's on the product side as the oxidizing agent or the reducing agent. Think about it as in like past and present tense. Like past tense, I had an oxygen. Present tense, I don't have an oxygen. So I was, you know what I mean? So anytime you see oxidizing or reducing, you better be looking at the reactant, left side of the equation, okay? If you're oxidized or you've been reduced, you're a final product, all right? Unless we're talking acid-base chemistry, we wouldn't be then talking about any of this, okay? Because acid-base chemistry is reversible, all right, for the most part. So this stuff is either going to be happening on the left side or the right side, and just be able to identify those terms, okay? Because he might not even give you the O2 molecule happen, and then you can easily find it in the chemical equation. He's going to say, tell me what the oxidizing agent is, okay? Also, another big hint, why do I always do that? Big hint is if you're the oxidizing agent, I can tell you right now that you didn't get oxidized. So please do not pick if you have Fe2O3 and then you have on the right side an Fe. Fe did not get oxidized, okay? And that's the biggest thing for people to understand is they always want to follow iron. Look at what happened to iron on the left side, and then look at what happened on the right side. Well, if iron on the left side was the oxidizing agent, then on the right side, he must have been oxidized. That never happens. If you're the oxidizing agent, the opposite happened to you in the products you were reduced. If you were the reducing agent in the reactants, then you got oxidized in the product, okay? It never, ever, 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 if you're the agent, it never does it to itself. Does that make sense? If I was a secret agent, would I go out and assassinate myself? That's ridiculous. That's the silliest thing I've ever heard. But so maybe it does happen, okay? But that's the kind of thing you need to think about. Who's doing the attacking? You don't want to attack yourself, okay? All right, so if we're talking about oxygen, if I lose oxygen then, was I oxidized or was I reduced?
You were reduced?
Yes. If I gain oxygen, I was
Oxidized.
perfect. I know it sounds silly to answer these questions, but trust me, the more that you say it out loud and do it and talk and answer, the easier your exam will be, okay? If you lose hydrogen, are you oxidized or are you reduced?
Oxidized?
So if we lose the hydrogen, did I put an arrow? If we gained a hydrogen, then we're what? Reduced. Okay. That is really weird for people to think about, but think about it. That's why this is a threefold definition, because you're going to figure out what works best for your brain. For me, right away, if I think about if I gain a hydrogen, I'm reduced, I immediately am thinking of charge, which is why I present to you the electron definition, okay? So you can follow the source of electrons and protons, okay? Following the charges. So if we lose a negative, that means we're being what? Becoming what?
Oxidized?
So if we lose our electrons, are we becoming oxidized or are we becoming reduced? One more time.
Oxidized, right?
Right. So if we were here and I lost my electrons, then I would become positive, and then an OH comes in, or any source of O negative is going to come into what that plus came, and I will be oxidized. Okay, a lot of people use Leo goes GER or oil rig. Oxidation is loss, reduction is gain, or lose electrons, you're oxidized. Sometimes that works for people, sometimes it doesn't. It just depends on what you're looking at, okay? If you're following the proton, it might seem weird. If you're following the oxygen, then it could seem fitting, okay? It just depends on how you look at it, so you need to make sure you're aware of all three of these, because you'll notice, if we look at the lose, 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 one lose is reduced, but the other are oxidized. And then if we look at the gain, again, one is oxidized and two are reduced. So you can see how, depending on where you're looking at, the source of our oxygens and our electrons, these kind of things, this oxygen, looking at the oxygen and looking at the electrons, they're opposite, right? And so it can kind of get a little mind-boggling, okay? But this is the biggest part for oxidation reduction reactions, okay? You're going to be given an example that's going to have a clear as day oxygen. You're going to get an example on the exam that will have a clear as day source of hydrogen. And you will get an example on the exam that will have only electron pushing. So you need to be able to do it all three ways from all three of these definitions and understand what is being reduced and what is being oxidized, okay? So right there is 3 questions. 3 questions on oxidation. Okay, go to the bathroom. Go to the bathroom. Go. Okay, so make sure you know that. Backwards and forwards. Go. All right, now we're on 5, chapter 5. Okay. Oh, we're still chapter 5. No, but we're on a different part of chapter 5. The biggest another last thing on chapter 5, I think that you'll have to do is I think it just reminds me. I think it's endothermic, exothermic reactions. I think that's the end, right? Of 5. Energy, free energy.
Yeah.
I think that's it. Yeah. Okay. So energy diagram. So we call those reaction coordinates.
You forgot a G in energy.
I know. I'm horrible. Just let it go, right? I'm just gonna go this. I'm just gonna do this because I'm horrible at spelling, especially fast. But thank you.
I'm just messing with you. It's okay.
I'm literally the worst. I taught Calc 1 and 2, and they hated it because I'm like, sorry, you don't know what that is? Oh, I'm sorry. Yeah, don't even. No, I can't. I'm gonna do the energy. Okay, so the thing that you need to be able to do from here is you need to talk about, I don't know, but I'm gonna prep you in case he does it. First of all, he might, for the sake of this ease, I'm going to put them together, but they might be separate for just extra questions. You could have something that's like this. Then you could have something that looks like this. Okay. Actually, I'm going to do this a little bit like this. Okay. Okay. You'll have to be able to identify whatever's in the dots here. So there's the first one. Here's another one. He'll already have it labeled usually as this. And then here he's going to have energy. This is going to say reaction coordinate. And then the couple of things that he's going to ask you about is he might say, if he labeled this as A and this as B, which is spontaneous? Which is endothermic, right? Which is exothermic? Which happens faster? What is the symbol for Gibbs free energy? What is this? Okay. So if we were looking at this kind of reaction, I'm going to pull up the picture of one of them he did. Sorry, double computer, hang on. I don't like I can make up question, but I'd rather use an old question in case he reuses it, which he does a lot of the time. Okay. So if we had a, if we're looking at A, which is the red line, is this a spontaneous reaction, yes or no?
No.
Okay, why?
Because it has a high, actually, I guess activation energy is not that high, but the energy of the reactants is lower than the energy of the products.
Bang, okay. The first thing that you fixed yourself on is the exact point that I want every student to know that every student makes, okay? Stay away from activation energy and free energy. They are not the same thing, okay? Free energy and energy of activation, E sub A, are not the same thing. E sub A is how much energy do I need for the reaction to go from reactants to products. Free energy is how much energy do I have in the system? okay? So if you have a lot of energy in the system, can I do something more easily than something that doesn't have energy and requires such input? Okay. That's how you need to think about it. The energy of activation usually requires or is kind of often associated with catalysts here. Okay, so if he's talking about a catalyst in a question, then you're going to say, all right, I know I'm talking about the energy of activation because catalysts are the only thing that can lower that. Okay, they're the only thing. Why? Because catalysts speed up the rate of the reaction by lowering the energy of activation. Okay, there's a threshold for everything, right? And that's what it is. And when like a battery has enough charge, then you can power an electronic. That's the same thing here. If there's not enough energy, you're not going to be able to start the reaction. Okay. Oh, Siri's mad at me. So energy of activation is E sub A. Yeah. Okay. Okay. So that's it. Delta free, delta or Gibbs free, which is delta E or delta H, right? What is it? Delta H, delta G, delta E? I don't even know anymore.
Delta
I think
G.
it's delta G.
It is. Okay, these two he'll give you because it's Gibbs. These two, this one is just the change in heat, the change in free energy, okay? So delta G is Gibbs, delta H is change in heat. Both are going to be used because when you're talking about heat, you're often talking about that's what's given off in an exothermic reaction because it's releasing it into the environment, into the surroundings, okay? So you're gonna see those two things used when we're talking about just the energy, the free energy, okay? And then catalysts for activation energy. The last thing that I want you to be aware of in terms of energy is our laws of thermodynamics. So you need to know entropy and you need to know enthalpy for this exam. Those are two more vocab words that you need to know. Pardon me, I'll be right back, 30 seconds. Sorry, I had to tend to my kid. All right, that's it. That's all you need to know. So all of those questions you need to be able to identify from a graph, or all of those questions you should just be able to choose the best option from a multiple choice, okay? So the picture may be there, it may not be there. The picture also may be separated into two different pictures, one showing an endo, one showing an exo, but it's the same concept, okay? So as long as you know all of those bullets, you'll be good for this equation, okay, or for this part of the exam. Okay, and now I think that's it. I'm looking now for chapter 5. Okay. Okay, wait, I'm going to toss in this last thing. What is the minimum amount of energy that reactants need for molecules to be in the correct orientation? What do we call that? The minimum energy that reactants need for molecules to be in the correct orientation.
Isn't it like the threshold? Is that right?
The threshold. So what is that threshold telling you though? What's the name of the threshold that we just talked about?
Is it orientation or is it the entropy?
So entropy is our randomness, right? That's dealing with the collision of molecules.
So is it just the orientation?
So yeah, so it's asking, what do we call that? So when molecules, the minimum amount of energy that we need for those molecules to be in the right orientation, what is it called? The minimum energy.
Is it the activation energy?
Yes, the activation. Okay. Do you see how he's trying to literally punish you? Okay, he's punishing you. He's playing mind games. The minimum energy, that's literally the only thing that you needed to get on there. He's going to add, but then the first thing as a student is we're going to read the question and then immediately go to the multiple choice and we're going to see collision. energy. And we're going to see disassociation, and then we're going to see orientation energy. No. Okay. What we do want is, if there's more randomness, entropy, law of thermodynamics, if there's more random chaotic movement inside of a reaction, that means that the chances of our molecules colliding into each other goes whoop, 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 through the roof, which means then we don't have to do add more energy, right, to get them to make products. Okay. So if we increase the randomness, increase that random free energy of entropy, increase the energy, get those molecules bouncing, that means we have a lower activation energy, because they'll be, for every one time they were bouncing and hitting each other, we added more energy. Now they're hitting each other 10 times more, which means that's going to definitely lower the chances of them not creating products. Okay. That's activation energy. Activation, activation, activation. Okay. It's activating the products. That's how we get there. There we go. 2 products. Okay. All right. And all right, up here. You're going to see that word on the exam. Okay. All right, and then chapter 6, I'm just looking at the exam. So chapter 6 is last. This is all you need to know, sugars. Sorry, I will talk in a minute. I'm just trying to write. Why did I spell it that way? Oh my gosh, that's embarrassing. I'm gonna say location on carbon. And then I'm gonna also put, okay, for this part, this is what you have to know, okay? You need to know about alpha and beta anomer, and you need to know about your glycobonds, so your glycosidic linkage. You need to know where those linkages occur. And I will tell you right now, it's a specific numbered carbon, okay? That's what he's looking for, which one. So for example, you'll be given a question that looks like this. Let's say we have CH2OH, and then we have something that's like this, and then we have this, this, this. Okay, I'm not going to draw them in yet. And then I'll redo it. 1, 2, 3, 4. Okay. When we're talking about alpha and beta anomers, we're talking about which carbon. Actually, I'm going to put on here too, up here. I'm making one more. Fisher projection. For the Fisher projection, you're already going to be presented it in a Fisher projection, and he's going to say, this is a Fisher projection of blah, blah, blah. Which one of these is an enantiomer? Which one of these is its, and he'll just tell you which one of these, and then he'll do the image a couple more times, is an enantiomer of the Fisher projection. That's what the question is going to say. So from that, all you need to know is what does it mean for something to be in an enantiomer, which you should know by the end of chapter 4. And then you should be able to find what that image would look like from a Fisher projection. Okay. So a Fisher projection, by the way, is just dealing with a cyclic sugar, and it's just kind of putting it in a linear form. So please don't get confused when you're looking at sugars in general, because a lot of students don't connect the dots. When we see sugars always drawn like this, that's a Fisher projection, but we never call it that in biology because we don't really like to be chemists in biology. But when you see sugars like this, that's a Fisher projection. Okay, this is a carbon. That's what it is. Okay, but we just don't call it that. So I just want to let you know that anytime you see a molecule of sugar built like that, it's a Fisher projection. Okay, so for an enantiomer, an alpha enantiomer, we have to the first thing that you want to do when you're looking at the sugar is, can you tell me where carbon 6 is?
Someone in the air,
The one in the air?
or just
So
above, I guess I should say.
This one, right? Yeah.
Sorry,
Okay.
I was drinking this.
Yeah, good, good. No, I'm glad. Okay, so that's carbon 6. And then from here, do we count this way or do we go this way or what?
Counterclockwise.
Okay, so always follow the carbons. Okay, if you go this way, you're going to be running into a C double bonded O, okay, a carbonyl. So let's go ahead and 6, that's 5, 4, that's 3, that's 2. Did I do that right?
So no, the 5 carbon is actually underneath the 6.
Exactly. Okay, so when you're labeling these carbons, make sure you either dot each one, okay, or that you double check, because a lot of students move super fast and then they're like, well, Liz, this is 2, where's carbon 1? How do I have a 6 carbon thing? Okay, so always make sure that you label right. Okay, carbons are the first thing that everybody misses. Okay, so now we need to fill in our OHs. So this one is down, this one is up, this one is down, this one's down. Okay, so only thing you need to know for this to determine if something is alpha or beta is this right here. So we're on carbon 1 and the OH is below, okay? Right, or in this way, it's actually behind kind of a thing, but neither here nor there. So we'll just, for spatial awareness, this is definitely below, okay? So you need to know for it to be alpha, that you better, it's always, the glycosidic linkage is gonna occur at C1, which is carbon 1, and it's the OH is underneath what you would think, okay? So then the opposite is for a beta. So 6, 5, 4, 3, 2, 1, okay? And then we'll go ahead and fill it in with this color this time. So this guy is still below. Sorry, that's this one. All of the other preceding OHs are the same, okay? None of this actually even, we don't really even care what's happening here in terms of where those OHs are. You can just kind of negate that, all right? You just need to focus on what's happening at C1 for both to make that determination of if we're alpha or beta, okay? So this is C1 again, but the OH is going to appear up, okay? As far as cis and trans go, the only thing that I really want you to know about that is just what it means to be cis or trans. I don't think that he's not going to tell you cis or trans in terms of alpha and beta sugars, but Mastering Chemistry kind of does that. And then if you proceed to do other things on the internet and look at other practice things or other TAs, they may talk about that. You don't need to know that for the exam. The only thing that cis or trans may come up on is if we're talking about structural isomers. So I'm going to go off the side here, and you might have something that looks like C2 let's see, I'll draw it first before I decide what I want to call it. This will work. So you'll have it be C2, and then he'll say that's going to be H2, F2. Okay, or he might place that F, one F here, and then put another F here. Okay, or do something weird with the C's, because sometimes technically when you name this, it would be a C, H, and then he'll do this. Okay, and he'll put the C's on the outside to trick you. Okay, so when you do that, when you do something like this, this is the only time that cis and trans will come into play, is a structural isomer, because you have to ask yourself, how many different ways can I draw this? Okay, and you could actually draw this way. And you could draw it this way. Okay, and the only thing that we're looking at is for something to be cis or trans or neither, is where do they lie on the plane? Okay, so the plane is always going to be the measurement is always going to be this double bond, okay, because double bonds don't move in space. And so the fact that there's a double bonded carbon here, he's restricting things, okay? So when you're deciding where things lie, if they're on this, if you can draw a circle between one of the double bonds and then the two substituents are the same, that's cis. Okay, you have to be able to include a double bond there, which is automatically going to make us see that this is nothing. That's what we like to call garbage. Not the molecule, but that's just garbage. That's just a garbage thing to put in for an exam. Okay, for this one, the thing here is, even though it doesn't look like it, this is still really getting one of the double bonds, and that's trans. Okay, so it makes a cross. Okay, opposite planes. Okay, so trans, cis, and that's nothing but garbage. Alrighty, so don't get straight. That's the only thing about cis and trans that you'll need to know for the exam. And I probably guarantee it'll be close to this example. Okay, so that's it. That's the exam. That's all you need to know for the exam. How about that? We did that in about an hour. Okay. Is there anything now that you would like me to walk through in like one example or a little bit of a deeper understanding? I don't want to keep you on here for too long, because I think that doing it this way allows you guys to go on your own time, fine tooth comb this list that I've provided, and then you can determine what you need to work on and either reach out to me for examples or find them on your own or whatever that may be, or only come to part of the review tomorrow. But is there anything on here tonight that you'd like to cover or reiterate or go over?
I was wondering if you could go over an oxidation reduction reaction, and maybe the one you were talking about with iron.
I can do that. Sorry, I'm looking at my old notes so I can find a good example. Okay. Also, if you didn't write all the stuff down tonight and you're one of those people that are just paranoid about that, email me and I'll send you the PDF, okay? So some examples of oxidation reduction. Yes, let's do it. Let's do it. So iron, right? So this one I'm going to put as a mark as a 1 because if you go back to the oxidation reduction, like the definitions, I labeled them 1, 2, and 3. So that's kind of where you can look and see, okay? So for 1, we're talking predominantly about oxygen and only looking at the oxygen. So if I had something like, let's do this one. Okay. If we did, okay, I'll do 2 of them. This is the first one I was talking about. So we have Fe plus O2 yields Fe2O3. Okay. In this case, right, this one is really tricky for students to kind of see what's going on because we're like, well, what is happening here? What's doing what? I strictly have oxygen here, and then I only have iron. So in this case, right, who is doing the oxidizing?
Isn't it the oxygen?
Exactly. It's no trick question. Okay. It is the oxygen, right? But the thing is you're going to be like, okay, well, what? And he went from a 2 to a 3, right? And you can see that if you're adding, are you getting more negative or more positive? So he's a +3 now. His oxidative state is +3. So did he get more positive or more negative?
More positive.
More positive. So if he's the oxidizing agent, then what does that mean happened to him?
He was reduced.
Beautiful. So then by just totally already deducing it, since we have 2 things, then this guy is the reducing agent. And he got oxidized. Okay. This one is like the simpler end of it. Another example that you might have is something that looks like this. Al 3 plus 3C. Yeah. I'm going to put this as this 2 and 3 because depending on how you look at it, it could be either way. Okay. What do you first know is not happening, is not visible here? What's not present? Yeah, exactly. Okay. So this is the one that students always miss. Oxygen's not present. Again, that's why I said, please, please, please know that definition by 3 ways, because this is still technically an oxidation reduction reaction, but we just don't have oxygen present. Okay. So what's happening here is who's being oxidized and who's being reduced.
So is the copper being reduced?
Copper is being reduced. So what is he on the left side? What is the name of that? What do we call it?
He's the oxidizing agent.
Good. Okay. Any questions on how we determined that? We solely looked at the charges. Okay. Let's see if there's another one. I think those are the two that he uses quite frequently, to be honest with you. So I think I'm going to stick with that to just for ease because he's a repetitive individual. So I think those two, even if we changed out aluminum to something else, it would still be this. It would still be the same thing because we're talking about we're dealing with our, you know, the group metals. So group 1 and group 2. Okay, so that's really not going to change here in terms of if I changed aluminum out to something else, as long as you were dealing with group 1 and 2 metals. Okay. What other questions do you have? I guess I should do this too for you. Here's a very blatant number 2. So this was more like a 3. I should label this as like definition 3. Here's a blatant 2 definition. If you had something as zinc plus 2H plus yields to, well, it'd just be Z. Okay, so this is blatantly talking about hydrogen now. Who lost the hydrogen? Who received the hydrogen? Okay, but that's how they're going to be formatted. Blatantly obvious, oxygen present. Blatantly obvious, hydrogen present. Not so blatantly obvious, but still in oxidative reduction. Okay, does that help? Does that clear things up? Okay, because this is the hardest one here for students, is this guy. They're going to think that something else is happening. It's a different type of reaction. But once you start taking these exams more and more and more, you'll notice that they're kind of built. He started to change a little bit, but they're built by chapter. So if you just did an oxidation reduction question, 9 times out of 10, you're still probably in chapter 5. And the next one is still going to be kind of about oxidation reduction. Okay. You feel the vibe I'm throwing out? It's kind of like that. Okay, so if you just did 2 oxidation reduction questions and then you have something that looks a little wonky like this, just follow the electrons. It's probably an oxidation reduction. Okay, because what other things have we done aside from oxidation reduction? Everything else, the only other thing that would throw you off is not number 2 or this second one in red. It would be this guy, because people would see H2 and they're going to think H2 palladium, but that's not the case. Okay. So really, where else have we done anything that looks like this outside of oxidation reduction? Nothing, because hydration, hydrogenation, hydrolysis, condensation, they're all water. See any water here? Negative ghost. Okay.
I have a question.
Yeah.
For like looking at this last one, you were saying like you'll find whatever is easiest for you. I mean, is it ever gonna let me down to just look at charge and decide, like, even with
No,
this?
I always look at charge.
Okay.
I always look at charge. I always only look at the proton source or the electron source, always.
Okay. Awesome.
But that sometimes is really hard for students to gather. So we like to kind of build them
Okay.
in a theory. I like to build them in a theory of 3-part definition. Start with your oxygen, then from your oxygen, stop thinking about it in oxygen and look at your hydrogen, because while they think it's hydrogen, that's still proton, right? Now we're into charge. We're in the first part of the charge, and then the electrons would be your negative. So it's a buildable definition.
Okay.
But yeah, you can't go wrong if you look at it in terms of electrons ever.
Okay. Awesome. Otherwise I'd start to like confuse myself if that's just like the easiest. All right.
Exactly. So again, that's why I like to teach them all 3, because it's not fair for me to only stick with one of them, right? Although I will say I really don't like oil rig and Leo goes GER. I really don't, because it's like, what the heck? You know, you're like lose electrons, but then we're dealing, where's the oxygen? And it's just like too much. It's too much. So I don't really like to use that a lot. Any other questions?
Could you work through the last problem you just wrote?
The zinc one?
Yes,
This one right
please.
here? Yeah, absolutely. So if we're looking at which one is oxidized and which one's reduced, okay? So I'm gonna scroll up just for a second to our definitions. And we know from that question, I'll just show it one more time. There is no oxygen present. You don't physically see an O, right? The only thing that we see is we see a lot of this and we see a lot of this, right? So if I see a lot of pluses and a lot of hydrogens, then I'm gonna go back up to my definition, my buildable definition, and I'm gonna see, okay, well, my second definition of oxidation reduction is dealing with where are the hydrogens going? And we know that hydrogens are always a plus charge. And then the third definition is where the electrons are going. And we know that electrons are a negative charge, but Liz just went down and drew a plus and an H. So we're gonna focus on what's happening with our hydrogen, okay? And if we lose a hydrogen, that means we were once positive because hydrogens are positive. Now we lost it. So now I get negative. And then if I was whatever status and I gained an H, that means I'm either got less negative, more positive, right? Because I don't know what's necessarily happening in terms of this gain per se. Because you could technically, if you were negative and you gained a positive, you'd be neutral, right? So I like to look at it, where are we losing it? Where are we losing it? Okay. So this zinc, all right, and let's take a look what happened to zinc. So zinc was neutral, and now all of a sudden he's got a 2+. So here he was neutral, or maybe he was negative. We don't know, because sometimes they don't throw those in there, okay? But 9 times out of 10, he was probably negative at some point, or had a higher positive. And now he's here. So what is happening here?
Lost electrons.
Okay, because 9 times out of 10, this guy, what's zinc's normal charge? Do we know? Do we know what zinc's formal charge is? I'll tell you what, it's definitely above 2+. Okay, so we know for a fact that he's getting oxidized, okay? And because he went from, if we just looked at this plain Jane though, for face value, and when I say face value, what's written on the paper, okay? Don't make assumptions. This would be a 0, okay? He went from a 0 and now he's +2, okay? So face value, from 0 to +2, he's gaining hydrogens. That means what happened to him?
It was oxidized.
Exactly. Okay. But if we think, so if you're losing, and the thing is too, though, is are we losing hydrogens, gaining hydrogens, right? You have to think about it. What's really happening? Okay. So he's oxidized. And then what happens to this hydrogen, this 2H?
It's reduced.
Okay. Does that help? So see what's going on in the reaction, see what's present, omit the obvious, and the only ones that are going to take you the most time are the ones that don't have oxygen present, okay? Because you have to look at charges. It's the easiest way. So if you start now practicing charges and you don't get reliant on the oxygens, then it sometimes is easier, but I only like to look at charge. That's the way I teach it, that I wish students would do, because the oxygens sometimes make us too dependent, okay? Especially when we get something thrown that doesn't have oxygen there. Okay, good question. What else? Oh, let's look at this. let's just do a random just real quick and test you. What is happening in this reaction? What's happening here?
Was that just an exchange reaction?
Yeah, nothing. It's literally nothing. Yeah, nothing. Okay. Yeah, you know, we could say it's an exchange, but is that on the list of things that you need to know?
No.
So you don't need to know it. Okay. But this could get thrown in there. And then as far as multiple choice goes, it will say neither, nothing. Okay. Just because we see hydrogens doesn't mean that that's automatically an oxidation reduction reaction. Okay. That's why we have to look at the whole entire thing. Choose the agent, pick what happened. Choose the agent, pick what happened. Okay. Cool. Any other questions?
Could we maybe just go through and fill out that energy diagram, like the bullet points that you had?
Yeah, for sure. For sure. I'll do it real quickly. I'll make a big one. And spelling police, don't scream at me anymore. Thank you. Unless it's like something really bad, but I'm just kidding. Okay, here we go. Here's one. Oh, that's horrible. Sure. Let's do this. Let's do this. A. B. R for reactants. PDTS products. Actually, I'm gonna use pink for that. That kind of looks the same. Okay. Okay, so this is what it's gonna look like, okay? Here is going to be E sub A, and this is also E sub A. Okay, so the first thing I think, no relative order, I'm gonna say which one is spontaneous. Okay, A or B? Which one would happen on its own?
B,
Why?
because it's giving off heat or energy.
If I was like, think about this, think about an endothermic reaction as this. I don't know if you have any CrossFitters up here, but you're like doing this, right? And then when you're going downhill, it's like this. Okay, that's what it would be like. It'd be like, hey, I'm falling off a cliff. That's like an endothermic reaction, even though that's not really what happens. I'm just saying it's going to be really hard for you to go down something that's straight, right? Okay, you're not going to really do that. But then in exo, it's like this, and then it's a nice snowball effect, a nice, ooh. Okay, so something that's more easy to get down, is it easy to go down something that's so super straight, or is it easy just to kind of glide down, right? So that's what kind of determines if something is spontaneous, is the ease and also the energy out. Okay, so yes, spontaneous is B. Okay, also because of just the way that the energy is coming out. We're not storing the energy like we are in A. Heat is staying inside there. Do you know how hard it is for us to keep our bodies warm? Could you imagine if we were able to keep our bodies warm? My Grammy would be very happy. Okay, that's a lot of work to keep the energy in. Otherwise, it just gets released. Okay. All right, the second thing I talked about was which reaction happens faster, A or B?
I'd say B again.
Why do you think that?
Because once it gets started, it keeps going.
Okay, let me throw out a common misconception. I'll do that in my favorite color. I don't care when I'm asking about which happens faster. I'm not talking about the right side on this invisible green plane. I'm talking about the left side. Who is going to start making products first, A or B?
So I guess it'd be A because the activation energy is lower.
Yep, bam, 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 bam. That is the answer that I'm looking for. Okay, remember, for a reaction to even occur, you have to get to the threshold. That threshold is known as the level, the energy of activation. Who's ever got the lowest energy of activation is going to go start the process from reactants to products first, meaning that's the quickest. Okay. Spontaneous does not mean quick. Okay. It just means who can do it without the assistance, who can do it more frequently, who can do it whenever, and doesn't have to be controlled. Okay, that's what spontaneous is. Quickness, however, definitely is dependent on your energy of activation. So and that's another thing to kind of tie in, how do we make reactions go quickly? By doing what?
Using a catalyst.
Exactly. So remember when I told you, when you think of energy of activation, to think about catalysis and catalysts, this is why, okay? So if he asks which happens faster, you need to look at right away, look at the energy of activation. If he says, which one happens more fast, or which one would benefit the most by adding a catalyst, okay? Who would benefit the most by use of a catalyst, A or B?
B.
B, because his activation energy is huge. So he would benefit most. That doesn't mean A can't use a catalyst, but it would make B go faster and potentially catch up to A if you started them at the same time, one without a catalyst and one with. You feel me? Okay. I don't remember all my questions. Okay, endothermic, exothermic. Okay, that one kind of goes with your spontaneous kind of thing. So which one of these reactions is endothermic? Endo meaning inside.
A.
Exactly. So then who's exo? B. And then the other thing is, what is the symbol for delta, for free Gibbs, for energy right there? Delta G, that's the symbol for Gibbs, free energy. There's the symbol for the change in heat. And then I'm going to label this as either energy of activation, which is why we call it E sub A, or you could just say it also is known as activation energy. They're the same exact thing. See, why do we teach it that way? I don't know, but same thing, okay? Anything else? Does that help clear things up? Any other questions? I'm gonna do, it'll only take me like 30 seconds for the sake of, in case people ask me for this PDF, I'm gonna put on here your functional groups that you need to know. But this is something that we'll go over tomorrow too. But in case you wanna get a jump start on studying, okay? I'm gonna cut these into two parts. I'm gonna draw a divider down here, okay? So. Okay, that's it. Those are all of them that you need to know. This one I will demonstrate for you here. It's really weird. It's just a carbon, 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 and then shh. Why are you talking about my file that way? Shh. Okay, that's literally how I remembered it, because I just was like, what the heck? How am I supposed to memorize this as like when I was taking organic chemistry? How am I supposed to memorize this? Shh. It's weird. Okay. And then ether is one that you definitely have to know, because this is what's going to happen to most of our, when we're talking about hydration reactions. Okay. Your ether, either this or you're this, ether. He's in, it's like a scale. He's in the middle. Okay. So that's how I remember ether. Amine, you're gonna have to recognize this, but it sounds like amino acids. And if you're familiar with amino acids, most amino acids have nitrogen or have a nitrogen in them. So again, that's what this does. It's just a alkane, and then you have some amino acid, a nitrogen, and then something else. It could be like a carbonyl, it could be anything else on there. Okay, we already know what alcohols are. And then these are just ways that we name carbons that are attached to each other. Okay, the alkane, we don't need to identify necessarily as a functional group, because then we would be listing everything as, oh, it's an alkane. Well, yeah, we already know that. That's why we give them special names like heptane, and specify that. So you don't need to say that you have an alkane functional group. However, the alkene and the alkyne definitely, because that's the source of more electrons. Okay, so you need to note those. All right, cyclics are just circles. This guy right here, need to know him the most. Why? Because he is literally the reason why everything else exists in the format that it does. He's basically the carbon copy. He's the carbon, he's like the main copy, and then everything else is carbon copies of it. Okay, so this is a ketone, right? And I will draw this as a Lewis structure so that you can see what I'm talking about here. What do we have right here? A carbonyl. That's a carbonyl, even though it doesn't look like that. Carbon's right there. Okay, so please don't forget that. This right here is what everything is based off of. The only thing that's changing from other functional groups is what lies on this thing. Okay, but this part of it will always be the same. That little kind of L that elbow will always be consistent for all the functional groups. Okay. Carboxylic acid is basically an alcohol on steroids. So it's an OH group on a carbonyl. Okay. So on this point right here, instead of a CH3 like it is for the ketone, it would be an OH. Okay. And the same thing goes for every other thing that you see listed here. The ester, the ether goes to an ester. How do we do that? Well, it's going to be this. Okay, carboxylic acid. I already said that. amide. Aldehyde. Aldehyde and ketones are the only two that students get messed up the most on. And here's how I remembered an aldehyde. H. Okay, he has to have that H on there. There is no carbon and then something, it's just an H, okay? So you have to have that on there. That's how he's different than a ketone, okay? And then the others we covered. Everything on this side of the list, you'll note, single chains. Everything on this side is still single chains, but single and double because we have the carbonyl. Okay, so really it's a double. Yeah.
So a ketone is always like landlocked by carbon, right? You're never gonna
always
have any. Okay.
Never. And I'll give you a perfect example. You're going to get something that looks disgusting like this on your exam. Okay. And then he might even just do like other things like this. Okay. You need a list, all identify all functional groups that are in this right here. Okay, so the first thing that I like to do is I avoid anything that's circular in shape because it always throws me off. I do those things last. First thing is identify the weird stuff. Well, this is really weird. What's that called?
Alkyne.
Perfect. What is this then? I noticed an OH here. So the first thing that you want to do on that is always follow it down. So OH, then I have a carbon and then a carbon and a carbon and a carbon, carbon. Oh, okay. So what is this?
It's just an alcohol.
Perfect. And then we're going to keep going. What the heck is this? CH3 OH. What is this?
An alcohol.
It's just an alcohol. Okay. That's just an alcohol. So you don't need to repeat it. Once you have one alcohol already listed, it's good. Okay. Then we're going to keep going around the circle. And then what is this?
What's the ketone?
Ketone. Fad diets. Keto. If you ever wanted to know, now you know. If you know, you know. And then now we've got all the weird stuff taken care of. Now let's big picture it. All right. Big picture, big picture. We've got this guy. That's a
Pentane.
pentane. Is that a functional group?
Nope.
No, just an alkene or a cyclic.
It's a cyclic, exactly. And I'm going to put that because I noticed that there's one over here too. Is this a cyclic?
It's an aromatic.
Aromatic, okay. If I had this on it, then what is it?
Phenol.
Okay.
So cyclic is going to be one of the question, like one of the possible responses then as a functional group?
Yes. Okay. It may and it may not. All right. If he's feeling weird, he'll put cyclic on there. If he's not, he won't put it on there. Okay. But you have to know that that is still, in fact, something that you would want to know, because what did we determine about cyclics? They're very stable. Okay. And so if we let our chemists know that we have a molecule that has a lot of cyclics in it, then we can say this is a pretty stable molecule, and we can just maybe attach something, a single substituent to it for just to hold it, and then we can remove it later to use during a later reaction. Okay, so it's important to know the stability of molecules, and that's why we like to list cyclics. But on the list of potential may not be, this one he may not do. He definitely won't list alkanes. Okay, never, ever, ever gonna put that in as a functional group. He might put this in. He might not, dependent. Just so that you know the difference that a cyclic is not an aromatic, okay? That they're different things, okay? Does that make sense? No.
It does.
Okay. Okay. But you'll be given like you'll be given like cortisone, or you'll be given a hormone, and it's going to be a big molecule like this, and he's going to say to list all the functional groups. Okay. We have to be able to do that. Anything else? Tomorrow we're going to do straight examples from an exam, so it'll be more like practical and application. This is just kind of going to give you the prep work that you need to do to come prepared to answer those questions tomorrow if you choose to attend, okay? This is like the quote study guide that everybody asks me for.
Thank you.
All righty?
So tomorrow, will you be recording tomorrow's session or no?
Tomorrow I don't record, and the reason I don't record is because I talk about past exams and questions used. So I don't like to post that on the internet in case he chooses to reuse them over and over and over, which he does. So I don't do that, right?
Sorry. So it's
this
tomorrow,
is the only one.
4 to 6. Sorry.
4 to 6. 4 to 6. Yeah. Correct. But if you really can't make it, just email me, okay? I won't give you like all of the problems because it'll be massive. There'll be like a lot of PDFs, and I don't pre-plan the PDFs. I kind of do it as we go, but I can get you, cut you some questions from it that you can kind of look to say, this is what you need to know. And it'll usually be the harder ones. They won't be the easiest ones, okay? Anything else?
Thanks, Liz.
You're welcome.
All right, see you tomorrow.
Yeah, thank you.
You're very welcome. You're welcome.